Hello, my name is Greg Gibson, and I will be presenting my slides for the lecture group project, Part D, slides 4.1 through 4.4, and slides 5.1 through 5.4. So, slide 1 here is the relevance of my problem. So, earlier in this project, we talked about gas behavior, especially the works of John Dalton, which was my relevant scientist, and Jacques Charles, which is obviously one of the major contributors to Charles' Law, if not the main contributor to Charles' Law. One thing Dalton did, he helped us understand gases as particles, and then Charles showed us that gas volume changes in proportion to temperature as long as the pressure remains constant. So my brand new problem is built directly off Charles' Law instead of using your typical balloon or piston example. I wanted something that you would actually see in real life. So I chose a scuba diver's emergency air cylinder because air cylinders definitely experience temperature changes as they dive deeper into the water. And it's just like how Charles cooled and heated gases in a lab where we see what happens as the temperature drops. And we'll get to see what happens when the temperature drops underwater to his emergency air cylinder. So the benefits of my problem, when it comes to understanding these kind of problems, it really helps build intuition about how gases behave. You aren't just memorizing formulas, you're actually applying them to something real, which I thought was pretty cool. You also practice skills like converting temperature units, Celsius to Kelvin, choosing the correct gas law, which is Charles' Law, and understanding proportional relationships, like how temperature and pressure, work together. And once you can actually solve this problem, it helps prepare you for other problems, like calculating how pressure changes underwater or how weather affects gas storage. So this type of problem helps build a strong foundation for more advanced gas behavior topics. So the development of my problem, when I made this problem, I started with the idea of temperature affecting gas behavior, because that's what Charles' Law is. But I didn't want something too simple like a balloon shrinking in a freezer, which is what probably the most common one you see. Instead, I wanted a situation where understanding temperature changes actually matters, because, that's your emergency air. If you run out of that, you're in a tough spot. The problem itself isn't too easy because you actually need to identify the correct gas law, and then you have to convert your Celsius temperatures to Kelvin, and then you have to follow multiple steps in order to complete said calculation. It isn't too hard. The math is pretty manageable, and the numbers are going to be realistic. So the biggest challenge when it came to actually developing this problem was trying to keep it from being too generic like your textbook problems might be. I just wanted to create something that might be a little bit more original, and it still teaches you the concept of gas laws. So the uniqueness of my problem. The reason my problem is unique is compared to common problems, textbook or online problems, they often use generic gas containers and simple numbers. Most examples are purely theoretical with no real-world context, which makes mine really stand out. What makes my problem unique is it's a real-world scenario where a scuba diver is diving in the temperature changes, so I think it makes it a little bit more engaging. It includes temperature changes in partially flexible cylinders, not just fixed containers. So there's a little bit of a caveat to that. It requires students to apply Charles' Law numerically and not just conceptually. You actually have to do some calculations to get your answer. So some of the steps included, you have to convert Celsius to Kelvin to make sure it's accurate. You have to clear initial and final conditions so students can solve independently. Added practical context to make the problem relatable. I know most of us probably aren't professional scuba divers. I'm sure not, but it's still pretty fascinating how temperature affects pressure, or how gases act in certain conditions. So it goes a little above and beyond. It tests problem solving and critical thinking skills. Because it's a real life situation, it prepares fellow students or even teachers for more complex gas law problems. And it combines it a little bit with diving physics as well. All right, so the graph for my slide here. My graph shows how the air volume inside the scuba cylinder changes with temperature. As the temperature drops, the volume also drops, and the relationship is linear because Charles' law shows a direct proportion between temperature and volume. So, I don't know if you can see that very well, but if you look over here, that's your temperature in Celsius, and then it's temperature converted to Kelvin. And you can see as the temperature goes down, the volume inside that air cylinder also goes down, which shows how it is linear, and if one goes down, the other has to go down. So each data point represents a possible real temperature a diver might experience. Seeing the line makes it easy to visualize the trend. Colder temperatures mean less volume, warmer temperatures mean more volume. Once again, shows you how they're proportional. This helps reinforce the whole purpose of the problem. Gas laws predict real behavior very clearly. Let's see, is there anything else on there? No, covered it pretty good. All right, so the formula for my problem. Here are some of the formulas and variables needed in order to solve this problem. The main one is obviously going to be Charles' law, which is going to be oh wow, they got this all sorts of messed up. I did not type this right. V2 equals V1, and then you multiply and divide temperature 2 and temperature 1. So all variables are used standard units, liters for volume and Kelvin for temperature. The Kelvin conversion is extremely important because you can't use Celsius in gas law formulas. So this slide just lays out everything needed before jumping into your actual calculation. This shows some of the variables in units. V1 is your initial volume, V2 is your final volume, T1 is your initial temperature, and T2 is your final temperature. Pressure is going to remain constant at all times, and you have to convert Celsius to Kelvin. All right, so my actual problem here, we're going to talk that through too, so we can kind of get an idea of what that is before we go into the steps for solving the problem. So a scuba diver, he keeps a small emergency air cylinder in his vest or her vest. On the surface, the air is warm, but once they dive into much colder waters, the air temperature inside the cylinder drops. Because the pressure is staying constant, the volume is allowed to change slightly inside the cylinder, and that lets us apply Charles' law to find the new volume. Once again, it's pretty cool because it's a realistic problem, which I thought was fascinating, and you can apply to real world scenarios, not just scuba diving. All right, so actually solving our problem now, we're going to choose the correct formula, which is V2 equals V1, and then T2 divided by T1. So you have to convert temperatures to Kelvin. Temperature 1 is 28 degrees Celsius, and then you add Kelvin to that, which is 273.15, which makes our temperature 1 301.15 Kelvin. And then we take temperature 2, which is 4 degrees Celsius, add the 273.15, which equals 277.15 Kelvin. So now you have to substitute the values. So V2 equals 0.750 liters, which is our volume. And then you take 277.15 Kelvin and divide that by 301.15 Kelvin. You have to compute the ratio, so you do your division first there. 277.15 divided by 301.15, which equals 0.9203. And then your final calculation, V2 equals your volume, which is 0.750 times the 0.9203, which equals 0.690 liters. Your final answer is going to be that 0.690 liters. And you can see the formula right down here at the bottom, which shows you how to convert that properly. All right. All right, so now we have to verify the formula and make sure it's actually correct. So to confirm that the answer is correct, you have to check a few things. First, the temperature, it decreases. The volume should also decrease. And our answer clearly shows that. Second, the math checks out because the ratio of the Kelvin temperatures matches the ratio of the volumes. The units also make sense because we stayed in liters for volume and converted temperatures properly. Finally, the solution ties back to the main ideas from the project, showing how Charles' law and basic gas behavior apply to real-world situations like scuba diving. This reinforces exactly what Dalton and Charles discovered about gas particles and temperature. So that is my Part D submission for the lecture. Thank you very much.